Vapor compression refrigeration cycle. The four basic components of vapor compression refrigeration cycle are compression, condenser, expansion device or throttling device, and evaporator. These are the four basic components. The function of compressor is to increase the pressure of refrigerant. When pressure increases, simultaneously temperature also increases. Condenser is nothing but a heat exchanger which will release heat from hot refrigerant to atmosphere. Throttling device is a device in which passing through which the refrigerant pressure will decrease and simultaneously temperature will decrease. This less temperature, less pressure refrigerant will enter into evaporator, that is also a heat exchanger, from where cooling will happen. So the less temperature, less pressure refrigerant when enters into evaporator, this particular portion is a cold region from where we want to release heat. So this heat is taken by refrigerant, this region will become cool, and then again it will enter into a compression, and this cycle will continue. This particular cycle is called vapor compression refrigeration cycle. This cycle we will understand on two different diagrams, that is called temperature versus entropy diagram and pressure versus enthalpy diagram, one by one. This diagram is temperature versus entropy diagram. Let us understand the different processes here first. This is my peak point on TS diagram. If I follow this line, that is the left side from peak point, this is saturation liquid line. If I follow right side line from peak point, that is called saturation vapor line. The region here, the left side of saturation liquid line is a liquid region. Right side to the saturation vapor line is a vapor region, and intermediate in between these two lines, it is a mixer, that is a liquid plus vapor. Point 1, we assume that my first point is a saturated vapor line, that is a evaporator exit point. 1 to 2 is a process in which compression will happen, so temperature and pressure will increase. You can see here when my refrigerant comes out from evaporator after taking heat from refrigerated area, the state of that is 1, that is a saturated vapor, and pressure is P1. After passing through compression, it will reach to a pressure P2. When your pressure is increasing, simultaneously temperature is also increasing. And 2 point is, you can see it is in a vapor region. So this particular point is a superheated vapor. 2 to 3 process is a condensation process, means my refrigerant will enter into a condenser. It will reject this amount of heat first, that is called heat of superheat. It will become a saturated vapor, then it will reject latent heat, and it will come to point 3. This process will happen at constant pressure, and third point is saturated liquid point. 3 to 4 is expansion process, in which enthalpy remains constant, entropy slightly increases, and it will reach to a point 4. We can see here the fourth point is a liquid vapor region, means it is a mixer, not 100% liquid, not 100% vapor, but it's a mixer. And then it will enter into a evaporator from where the refrigerant will take heat from the refrigerated area, and it will run through saturated vapor point. Same processes we will plot on pH diagram, that is pressure versus enthalpy diagram. 1 is a saturated vapor, 1 to 2 is a compression process, 2 to 3 is a heat rejection, 3 to 4 is expansion at constant enthalpy. So 4 is constant enthalpy, and 4 to 1 is heat inlet or refrigeration effect. These are the two applications, basic two applications of vapor compression refrigeration cycle. One is a refrigerator, one is an air conditioner. You can trace the component here is a compression. It will enter into a condenser, then expansion device, then evaporator, and again the refrigerant will come to a compression. Here also this is a compressor, condenser, expansion device will be here, and then it will come to evaporator. This portion will be inside your room, which will give you cool air into a room, and condenser will be outside so that heat will be rejected into atmosphere. Now let us come to a calculation part. If I want to do a calculation of simple vapor compression refrigeration cycle, I need to have a 4 different point 1, 2, 3, 4. First it exit from evaporator, exit from compressor, exit from condenser, and exit from expansion device. If all points are known to me, with respect to temperature and pressure, we can calculate its enthalpy, either using a property table or using a chart of particular refrigerant pH chart. We'll get H1, H2, H3 and H4. Once we have all the values known to us, we can do calculation. Let us start with this. Suppose I want to calculate refrigeration effect, cooling effect. So this is a particular portion where the cooling happens. That is the evaporator. So the refrigeration effect or cooling effect, if I want to calculate, that is nothing but mass flow rate into delta H, H1 minus H4. Now compression work will be 1 to 2, in which mass flow rate into delta H will give you compression work, and heat rejection is mass flow rate into delta H here, that is H3 minus H2. It will be a minus as it is heat rejected, or you can multiply mass flow rate into H2 minus H3. The coefficient of performance of VCR cycle is refrigeration effect divided by compression. Refrigeration effect we already know, compression effect already we know. If you take ratio of this, it will give you the coefficient of performance of VCR cycle. Let us understand by some numerical values. As I mentioned, H1 is enthalpy of saturated vapor at given temperature and pressure. H2 is enthalpy of superheated vapor at given temperature and pressure. H3 is enthalpy of saturated liquid at given temperature and pressure. And H4 is equal to H3 as it is isenthalpic process or throttling process. We will understand now using R12 as a refrigerant. This is a pH chart of that, where this is our absolute pressure, that is in kilopascal, specific enthalpy in kilojoule per kg, and some temperature pressures are given. Using that value, we will calculate COP of this VCR cycle. My evaporator pressure is given 1 bar. My condenser pressure is given 10 bar. When refrigerant comes out from evaporator, its temperature is minus 30 degrees Celsius. After compression, the refrigerant temperature will become 60 degrees Celsius. After heat rejection into condenser, the temperature of refrigerant will become 40. And then expansion, after expanding, it will come to a 1 bar pressure and minus 30 degrees Celsius. So temperatures and pressures are known to me. Now I want to get enthalpy value of each and every point. This one point where pressure is 1 bar, so I can trace as it is in kilopascal, 100 kilopascal equal to 1 bar. I will make one line over here and minus 30 line. So this is 0 line, minus 10 line, minus 20 line, and this is minus 30 line. So intersection point of 1 bar and minus 30, if I extend onto enthalpy line, it will give me specific enthalpy. So this will be my H1. Same way, 10 bar pressure and temperature line equal to 60. This is a 60 degrees Celsius line. When it will cross this point, this will give me H2 value. Same way, H3 is a saturated liquid at 10 bar. This will give me H3 and H4 equal to H3. So this both H3 and H4 I can get from here. Once I have all this value H1, H2, H3 and H4, H1 equal to 338 kilojoule per kg, H2 is 380, H3 is 240, H4 is also 240. For simplicity of calculation, let us assume that my mass flow rate of refrigerant is 1 kg per second. We will calculate refrigeration effect, compression effect and COP. If mass flow rate is known to you, you can multiply here. The refrigeration effect is H1 minus H4, that will come to 98. 98, that is kilojoule per kg, and multiply with 1 kg per second. So kilojoule per kg into kg per second, it will be a kilojoule per second. Your answer will come into a kilowatt. Same way, compression work is m dot into H2 minus H1, that will be a 42. And coefficient of performance will be refrigeration effect divided by compression work, that will come to 2.33. Thank you very much for kind listening.